so small. Oh. No. Hello. Okay. Everything fine? Okay, I think it's time to start. So, any question from last time? Last time we were doing this review over the high school math of solving linear systems, but we give a more structured way to describe it. We were saying that if we have a linear system, then we can take out its coefficient matrix and we can take out the coefficient matrix or the augmented matrix, and then we have this very structured way to solve linear systems. That's the Gaussian elimination or Gaussian-Jordan reduction, where we get our coefficient matrix to reduce row echelon form. Then we say that if we get reduced row echelon form, then it's very easy to read the answers to your linear system. And I guess we didn't write down like a pseudocode for Gaussian-Jordan reduction. So let's try to write and maybe as a review, try to write them down here. Okay. So Gaussian-Jordan reduction, there are 3 steps. So first, so there is this general principle where you need to do row swapping when you are trying to eliminate things and your pivot is 0. Okay, so you need to swap the non-zero pivot into the row into your pivot row, and you start with setting your first row as pivot row and this as a pivot, and you try to eliminate those things into 0. Okay, so we have things. Oh, okay, that's not very good. Let's see what's a good way to draw this. Okay, so we start with first row as a pivot, and so we start with everything, and then we use the first row and the first row as a pivot row, first element as a pivot, and you try to create a whole bunch of 0 here. Okay, so you want 0, 0, 0, 0 here, and maybe the second row is also 0, so you will have a 0 block here. Okay. Okay, so that's a pivot. Then you choose the second row as a pivot. Now this is a pivot row. It was pivot row. And as we say, we want this to be non-zero, and then you eliminate all those things by row addition. Okay, and then you get a second block. So you have non-zero here and non-zero here. Then you have this block of 0 here, and you have something here. And so on the first step, at the end, you should get kind of this thing. So you have a non-zero starting point, and this part might be anything. It can be 0 or anything, but all the lower blocks should be 0. And this is like a kind of triangle. I guess it's not strict triangle form. Kind of triangular. We don't have a name for this, but kind of triangle form. Yeah. So we were talking about strict triangular form, but this is not strict triangular form. This is you are trying to get strict triangular form, but sometimes it's not strict. So kind of triangular form. Triangular form. Okay, so these are the first step. 1. Then the second step is easy. 2 is, so you start with this thing, and maybe I should, yeah. Second step, you are just trying to make those leading number, which we say is non-zero, you will try to make them all 1. Because they are not 0, then you can multiply each row by their inverse. Right, so you start with this thing, and it's non-zero, 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 non-zero. So you times the first row by 1 over maybe A1, 1 over A2, da da da. Okay. Is it too small? Maybe I just write the first row. Okay. So I want to multiply the first row by 1 over something, and each row do the same thing. Okay. And so what I want to get is I want to get row thing and leading with 1 everywhere. Okay, and so this is called oh, it's annoying. We don't have enough space here, so let me try to draw this smaller. Sorry. Okay. So second step. So let's say our thing look like this, and this is non-zero, 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 and we have each row 1 over A, 1 over A2, 1 over A3, and what we want to get is 1, 1, 1, something like this. Okay, and this is called row echelon form. Echelon form. Okay, and finally the third step, we want to get from row echelon form to reduced row echelon form, and remember those are all 0. And what we do is we take those 1 and try to eliminate things up to them. Okay, and so you have 1, 1, 1, and you're trying to eliminate up to them, then you eliminate up to them. Okay, and you should get by doing row addition again. You should get 1 and 0, 1 and 0, 0, 1, and other thing is whatever, and you get 0 here. And this is called reduced row echelon form. Reduced RF. Okay, we don't have enough space. Okay, so that's the Gauss-Jordan reduction in a very informal way, but that's the idea. So any question about this Gauss-Jordan reduction? You should be all familiar with this from high school math, but we're just writing down this in a more structured way. Okay, if everyone okay with Gauss-Jordan reduction, then let's go to the next topic. So we go to 1.3, matrix arithmetic. Okay, so as we said, so we motivate matrix as a weird way. We motivate it as a way to write down the coefficients of a linear system of equations, And by general, matrix is just this 2-dimensional block of numbers. So we have n by n matrix A, then it has n times m numbers. Okay, so those matrix elements, small a11, a1, a21 to am1, and all those up to amn. Okay, so the ijth element will be aij. Okay, and those entries are called scalars because they're just a number, and it's either real or complex number, but in this course we mainly deal with real numbers. Okay, and as we say, Aij will be the ith row and the jth column. Okay, and so there are notations to this. Okay. So this Aij notation is a little annoying because you need to find a different symbol for all the elements, right? So you have big A for the matrix, and we have small a for the element of the matrix. But so sometimes it's easier to just write big Aij. Okay. So this is not a book notation, but sometimes we'll do this, and you will also see this in other sources, and we're soon going to see this, but yeah, it might be confusing. So sometimes it will be confusing. So you want a parentheses over your matrix, and also there is another notation for the element of matrix as A of ij. So this is more like a programming thing. So for example, if you try to use MATLAB, although we don't force you to do MATLAB, but you should still learn a little bit about how to do the calculation in MATLAB. Yeah. So like in programming, then you can think about this A as just a two-dimensional array. Then you will see the ij's element in just the indexing, and often you will write in this way. Okay. So anyway, all those Aij, big Aij or small Aij means the element on the ith row and the jth column. So there's an Aij somewhere here. Okay. Let's write that. So there can be an Aij somewhere here, Aij, and so this is I and this is J. Okay, so that's Aij, and we also have this notation that's a big word of indexing elements. So this big Aij or small Aij is you take a big matrix and you try to look at element. And we can also write the shorthand as, so we think about if we have all those small Aij, then how do we describe the matrix that's the collection of them, and that's this notation. We put parentheses around this small Aij, and that means big A is a matrix that's determined by all those small Aij. Okay, so that's just a notation. And so we have a matrix, then we describe vectors. So, yeah. Is this working? Yeah, so vectors are actually easier than matrix. So we think vectors are just a smaller matrix. One of the matrix dimension is 1. So we can have row vectors that's just 1 times the matrix. So the height is 1. Okay, and here there is actually something important. So because of more notation. So notation we use this book, we're distinguishing between row vector and column vector. Okay, so row vector we write it as this bold case but lowercase number, and with the vector sign up here. And similarly, we have column vectors. Column vector just has a width as 1 here. Okay, so this width 1 matrix is a column vector. And for column vectors, we use this bold lowercase later, but without the vector sign. Okay, so yeah, so column vectors are returning this kind of notation, and the row vector returning this kind of notation. Okay, and then here we give you a very different concept, the concept of vector. Well, it's kind of like vector space, but we haven't talked about space more. But anyway, we define the Euclidean space as the set of all matrices that have real numbers. Okay, and I guess it's a set of all column vectors. Okay, so Euclidean space is a set of all column vectors, and it's parameterized by some n, so that's the dimension of the space. So n-dimensional Euclidean space is a set of all those n-dimensional real numbers. Okay, so Euclidean means real, and we have n-dimension, that means the matrix has n element here, and it's written as Rn. Okay, So that's Euclidean space. It's important to remember what it is. And okay, then we think C is a little more interesting. So the matrix is a vector, then we can view matrix as a lot of vectors. This is basically doing nothing. It's just how you look at your block of numbers, right? So, your matrix A is this rectangular block of numbers. Then you can cut your block into those strips, and then each strip will be a column vector. So you can think your matrix as whole bunch of column vectors listing together. Or you can also think your matrix as whole bunch of row vectors listing together. And but here we have a little more notation, so we say this is A1 vector, A2 vector to AN vector, or this A1 row vector, A2 row vector to AN row vector. Remember when we write those bold case, it's a column vector, and then we have those bold case with a vector sign, and it's this is a column vector and this is a row vector. Okay, so this is just a different way to partition your matrix into vectors. And but this is actually a little more interesting than this thing, because these things this means that you have those two different ways to how do you say? You have those two different ways to view your matrix as collection of vectors, and yeah. And sometimes they give you interesting interpretations, as we'll see today. Okay, but for now, this is just you cutting your block into strips. Okay. Yeah, and this is just what I say. So those row vectors we denote by this small case A vector, and those column vector, or those small case A vector. And yeah, so this is just this in more detail. Okay, so hopefully everyone is clear with the definition. And we see an example. So we have a matrix A, that's this is 2 by 3, and so you can cut it into columns. So the A1 vector will be the first column vector, A2 a second column vector, A3 the third column vector, and you can you can also cut into those row vectors. Okay, so nothing really changed. The first row is this row vector, and the second row is this row vector. Okay, and now we go to a little more algebraic part of this section. So we say two matrices are equal, so A matrix A and the matrix B, A equal to B. So first, okay, so we already say something here. Okay, so we skip here, we kind of sneak in a little thing we already say. So first, if they are equal, then they must have the same dimension, otherwise they cannot be equal. Okay, so we say those two matrices with the same dimension are equal, then then that means all of the coefficients are equal, right? And that's pretty obvious. So all those Aij equal to Bij. So I guess we can write, this is kind of trivial, but we can write a little picture. So this just means that you have an A matrix and a B matrix, and they have the same dimension, although the drawing is a little wrong. And I'm saying for all Ij, so all those entries are the same. Okay, so they are looking totally same, so they are the same. Okay, so that should be pretty intuitive. That's equality of matrix. And then more algebra, we can do scalar multiplication on the matrix. Okay, so we have a matrix, we have the block of number, and then we define this alpha times A. So alpha is scalar, is a number, so probably a real number here. And we define alpha times A means that you multiply alpha on every matrix element. Okay, so every Aij become alpha Aij. Okay, so here is the example. So your A is this matrix, then you times alpha is 1 over 2 here, alpha times A, then you just multiply 1 over 2 on all the elements, so everything got divided by 2 here. You can see that 10 divided by 2 become 5. and or you can multiply by a bigger number, 3 times a, then everything times 3 here. Okay. Should be pretty intuitive. And matrix addition is also pretty intuitive. So A and B two matrix, and addition is only defined when both of them have the same dimension. And then A plus B, yeah. So the addition we just write as A plus B is another matrix of the same dimension, and it's just the entry-wise you add A and B together. So it's easier to see an example. So you have A like here and B like here, then A plus B, you just see every element together. So for example, this 1 element is this 1 element plus this 1 element. So 3 plus 2 become 5, and 5 plus 2 becomes 7. Okay. So the addition and the multiplication by scalar are all defined entry-wise. Okay. And here is another example. We have a vector, but a vector we see as matrices. So you add those two matrices together, then 2 plus minus A become minus 6, A plus 2 become 10, etc. Okay. And now we have multiplication of scalar and addition, then we can define subtraction. So A minus B you just define by A plus minus 1 times B. And you can see that this is the same as you just do entry-wise subtraction. So like A minus Bij will just be Aij minus Bij. Okay. And then we are talking about addition now, and then we can write down this identity of addition that is 0. So we can have the 0 matrix. Okay. So we don't usually use these too often, but anyway, in this course we use this big O to represent the matrix which have all entries being 0. Then yeah. So it's a matrix where all entries is 0. It's just a whole big block of 0, and it's pretty boring. So if you add any matrix with 0, then that will be the same matrix itself, because for the entry adding 0 doesn't do anything, and so you can add from left and add from right to the matter, and it will be 0. And also we have identity, then we can think about inverse, and we see that everything has the inverse of minus A. Okay. That is, you have the minus 1 times A, and you add A to itself, then yeah, you can just do the entry-wise calculation, and you quickly see that you get 0. Okay. And so this minus 1 times A, we just write as minus A. Okay. Okay, that should be easy. Okay, then let's go to a part that's a little harder. That's matrix multiplication. I believe this is also taught in high school, but here we diverge from the book a little bit again, because the book is doing some weird way to try to motivate matrix multiplication without telling its rule. But I think it's very confusing, so let's just define matrix multiplication first. Okay, and so matrix multiplication is you want to multiply a matrix with another matrix. So remember, so we had the multiplication before. Let's try to jump back. Oh, that's annoying. But anyway, so we had scalar multiplication. That's when you multiply your matrix with a number. So number is just 1 by 1. But now we have matrix multiplication. You want to multiply a block with another block. And okay, so it's not always possible. So first thing is it's always only possible when the number of columns of your matrix, so here we have a schematic here, so there's A and B here. So you can multiply A with B only when the number of columns equal to the number of rows in B. And you will see soon why we need this, okay? So this width here and the height here must be the same. Okay? And, but the other two numbers can be whatever. So the height here can be whatever, and the width here can be whatever. And we define matrix multiplication by saying that the new matrix, so I should write the name here. So think about this, A times B, and this is AB. Okay. And okay, so this is where we use our notation. So I'm saying the ijth entry of AB. Okay, so I'm defining AB entry-wise. Okay. Element-wise definition. So the ijth entry of AB is this weird sum. So this is something depends on the ith row of A and the jth row of B. And saying, so this entry is a summation, so we are summing some dummy variable from 1 to R. So we are doing this summation kind of through this and this, okay? So this is AIK. So the first element of those ith row times the first element of this column, and plus the second element of this row and the second element of this column, etc. And we want to do this summation through this whole row and this whole column. And this is why we need the number of the length of a row and the length of a column to be the same, because we want to sum over the same number of elements here. Okay, and okay, so that's the definition. And we are doing this in a little weird order. So we don't have an example, but we are going to see funny example here. Okay, and so now we go to the topic, go back to our linear system. I guess before I go next, any question about definition? Is we will see kind of example of why we want to do this. Okay, so why we want to do this? So this is a weird motivation. So we want to motivate on the linear system. So on the last section, we kind of motivate the matrix from the linear system. We were solving linear system, we go matrices by skipping writing the xi's. And now we want to do this funny thing of putting a xi back to the linear system. Okay. So we want to say our linear system is actually written on this equation of ax equal to b. Okay, so b is a column vector, x is a column vector of xi's, and a is your coefficient matrix. And let's see how this works out, and how it works with our matrix multiplication rule. Okay, so let's start with a very easy example. So our excuse me. So we have a linear system with only one equation. Okay, so the 3x1 plus 2x2 plus 5x3 equal to 4. And let's see how this can be written as ax equal to b. So our A, as we say, is the coefficient matrix, and so it's the 3, 2, 5 matrix, and x is this vector of your unknowns. Okay, so this is pretty algebraic. So this x is just your x1, x2, x3. It doesn't depend on equation at all. So ax, so we have 1 by 3 and 3 by 1. 1 by 3 matrix times a 3 by 1 matrix, and here we check, so we say our R need to be the same, right? So this R is 3 here, R is 3 here, is nice. And so here you see an example of our matrix multiplication rule. So so this is 1 by 3 and 3 by 1, and so if we back to, okay, so back here. So if you have n equal to 1, r equals 3, r equals 3, n equal to 1, so you should get a 1 by 1 matrix here. Okay, so it's just a number. Anyway, so this number will be, as we say, we want to sum over these products. Okay, so you have a 3 times x1, then plus 2 times x2, then have 5 times x3. Okay, so if you follow our matrix multiplication rule, you will get this 3 plus x1 plus 2 plus x2 plus 5 plus x3, and it's a number, although they are unknown equal number. Okay, and then we are saying this equal to 4, then so this ax equal to 4, then you get back to your equation. Okay, this is kind of algebraic manipulation. Okay. Okay. And yeah, so let's abstract this a little more. So you have one linear equation. This is a1x1 plus a2x2 dot 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 to an xn. Then you can write your matrix as this row vector of a1 to an, and your x as this unknown x1 to unknown xn. Then when you do matrix multiplication, you will pair this a1 with x1, a2 with x2, etc., and an with xn, and you will get this expression. So although there are lots of unknown, you can view this as a number, and you want this number equal to your b. So your ax equal to b. Okay. So this is our multiplication of matrix again. I guess it's the same motivation as the last section, but we are saying we can write this more precisely, so we are not missing an unknown. We are just concentrating on unknown into this x. Okay? And anyway, here we see an example of scalar product. So we see that if you multiply a row vector with a column vector, and they have the same dimension, they will get a scalar because, yeah. And so this is called scalar product or inner product. And they will see this more in a later chapter. Back to equation. So that was one equation, and what we have n equation like a natural system. So n equation, you have this a11, a12, a1, dot dot dot, and am1 all the way to am1 and 2 to an. And we see that it can still be written as this ax equal to b. So a is your this coefficient matrix, and x is once again this excuse me, unknown symbol vector x1 to xn, and b now is a vector because there are many b's, so b1 to bn. And then if you do the matrix multiplication rule of ax, then you see that, so ax is a vector, although this is really long here, but remember all those summation a11 plus x1, a12 plus a2 to a1 and to xn, we think this is a scalar. So this is a number. So ax is sorry. Oh, we have a typo here. Okay. So this should be m here. Okay. Sorry about it. Oh no, never mind. I confused myself. That's correct. Okay. Sorry, this is xn. Yeah. So yeah. So ax is actually an m-dimensional vector, and that's equal to this m-dimensional vector b. Okay. And yeah, so we can check the matrix multiplication rule a little. So the first element of this should be the first row times the first column, and so that will become that. So it should be okay. I should say the scalar product of first row and the first column, and the second element will be the second row times the first column, and then third element will be the third row times the first column. Okay. All the way to the nth element is the nth row times the first column, and there is no second column, so this only has one column. Okay. And then here you kind of see why we talk about the partition of A into row vector and the column vector. So here you see the partition into row vector is useful, right? So it's like each row vector is multiplying with this x and getting you some equation here. Okay. And yeah, as we see, okay, so this is what we were saying. So so the ith entry of those ax, so ax is m-dimensional vector, and the ith element is this ith equation ai1 x1 to ai xn. And that is the row vector times this the ith row of A times the x vector. Okay. And for example, we have this A equal to 421 and 537 times x1, x2, x3, and you see the first element should be this times this, so 4 with 1 and 2 with x2 and 1 with x3, and the second element should be this times this, and so that's 5 times x1 plus 3 times x2 plus 7 plus x3. Question? Okay. And then another example. Okay. And now, okay, so now is the example more like matrix multiplication. So if you're x, now we instead of unknown we put the actual number. Then you can have then those a times excuse me. Then a times x. Then you also have you have 3 elements here. So first row times this first column. Then you have minus 3 times 2 plus 1 times 4. And then the second element is the second row times the first column. And so 2 times 2 plus 5 times 4. Then the third element you have the third row times the first column, and it's 4 times 2 plus 2 times 4. And you do the elementary school math, you get this thing. Okay. And okay, more example. And yeah, so linear system equation, then you can write as this. Okay, so this more, I guess, mathematical rigorous form. So on the previous section, we just write this as a arithmetic matrix and try to do some row operation. But now we can write it in this more algebraic, more rigorous form. So once again, we don't want to write. So here we see that this equation is kind of this equation, but being a little lazy. So you still have the coefficient matrix here, and you have the answer vector here. And x1, x2, x3, we don't write it so many times. Okay, so we want to write x1, x2, x3 only once here, right? So here we are writing x1 3 times, x2 3 times, x3 3 times. So you can see this matrix equation kind of like a lazy way to write linear equation, because you don't write x1, x2, x3 repeatedly, you just write it once as a vector here. And then, yeah. And as our matrix and our matrix multiplication definition will say that this equation equal to this equation rigorously, because if you multiply all these matrix vector multiplication, then we can see this as a vector, and all of the elements will be just the same. Okay. So this is the motivation of why we want to do. Why we want to define matrix multiplication in this way, because if we do this, then we can write down linear sequential equation as this ax equal to b equation. And this ax equal to b equation, you need to write a little less of those xi's. Okay, and let's see a little more about this ax equal to b. And okay, so before we will kind of partition A equal to row vectors. And we see that we can also get an interpretation when we partition A equal to column vectors. Okay, because it's really hard to say, but AX is this vector of those A and X multiplying together. But we can also see this as whole bunch of vectors adding together, whole bunch of column vectors adding together. So we can, so yeah, it's pretty obvious from the drawing here. So we can see this as this vector plus this vector plus plus this vector. So we can see those as n column vector adding together. So and what are those column vectors is, and you see that all these column vector has x1 multiplying it, and all of those has x2 in it, and all has xn. So we can take all the xi here. So it's x1 times this a11, a21, to an1, and etc. all the way to xn of times a1n, a2n to an. And what are those a vectors? This is actually the first column of A, and this is the second column of A, and this is the third column of A. Okay. So this AX, we can also get an interpretation by partition A equal to columns. And then we see that it's weighted sum of its columns, and those weight are those xi to x1 to xn. Okay. And yeah, so ax equal to b, you can also interpret it in a column way. So you can think ax as a linear combination of columns of a and equal to b. And here is an example. So I guess we had, yeah. So we have those two systems, and you can think of this as a vector, a column vector equal to another column vector that we know. But this column vector, we can think of it as x1 times this 2, 5 vector, x2 times this 3 minus 4 vector, and x3 times this minus 2, 2 vector. Okay. And okay. And this is something we already treated in the talk before. So we have a linear combination of vectors. So, but yeah, it's just what you think it is. So a linear combination of vectors is that you have a whole bunch of vectors with same dimension, and you have a whole bunch of scalars. Then you can write this down. So you can multiply each vector with its corresponding coefficient. So a1 times c1, a2 times c2, and an times cn, etc. And you just adding them together, then it's called a linear combination of those vectors. Okay? And it's a useful concept. And okay, so that's the linear combination that we've been talking about. And yeah, so as we say, ax can also be seen as a linear combination of the column vectors of a. And with the coefficients being those unknown x1 to xn. Okay. And for example, then you can pick a number for your, so for this example, you can pick your x1, x2, x3 into some number, and this your linear combination will get something. Oh, here we actually write a solution. So x1, x2, x3 is the solution, and hopefully the solution is correct, but yeah, and you add those linear combination of vector together, you should get this 5, 6. Okay, and that means that this x1, x2, x3 being 2, 3, 4 is the solution. And we have another example where we have this x1 plus 2x2 equal 1, 2x1 plus 4x2 equal to 1 equation, and we can also think of this as a linear combination, but yeah, so this is linear combination, and but anyway, we see there is no solution. There is no assignment of x1, x2 that setting this equal to the 1, 1 vector, because the second element is 2 times the first element. So the ratio should be 1 and 2, and you can never get 1, 1. Okay? But really, this is just writing your linear equation in a different way. Okay? Okay, any questions so far? And anyway, okay, so we are back to the point where the book actually defines matrix multiplication. But and so we are defining matrix multiplication in a funny way. So we are saying we have matrix A and matrix B, and we can cut B into column vectors, and we are thinking about A multiplied with all those column vectors. And we know A multiplied with a column vector, you get a column vector. And you have n column vector here, and so wait, okay, oh, so down here I should B1, B2 to Bn. Okay, so down here I should swap the n and n. Okay, so this should be n by k, and this should be k by n, and this should be n by n. Can I do erase? No. Okay, and it should be n. Let's just write again, n by n. Okay, and anyway, yeah. So we have been talking about how you do matrix multiplied by a vector. Then you can think about matrix multiplied by matrix is just a whole bunch of matrix multiplied by vector listing together. So there should be n vectors here. Okay. Yeah. Okay. And so the first column of the answer should be a times b1, and the second column should be a times b2, etc. And the definition written again, this is a book definition of the matrix multiplication. It's the same thing except that they are writing a Cij for this AB. Okay. And yeah, so let's can look at this again. So we are saying the ijth element of the multiplication result is the I0 of A times the scalar product of I0 of A and the B column of J. And if you write down in the entries, is the summation K. So K here is getting sum over of AIK and the BKI. And finally, you can see more normal example without all the xi around. So example of just numbers of matrix multiplication. So we have A and B, the 3 by 2 and a 2 by 3 vector. Sorry, 3 by 2 and a 2 by 3 matrices. So you multiply them together, and you see the first element should be the first row times the first column and this thing. And say, okay, we want to say the second and the 2 element should be the second column times the second row. And here with the green thing, it should be, so it's 2, 3, it should be the second row times the third column, so 2 times 3 plus 4 times 6, etc. Okay, and yeah, and also you can have A times B, and you can also have B times A. And here it's possible because these three are actually the same. But now you see that A times B and B times A are different matrices. If you do that, so they don't even have the same dimension. Okay. And this is something important. So A times B not equal to B times A. We'll talk a little more. Then, yeah. Okay. And yeah, so here is another example. A equals this, B equals to this, and you have B times A and equal to this. Let's skip that. And but there is an important concept we want to say here. That is, the matrix multiplication is non-commutative. So A times B not always equal to B times A. Sometimes B times A is not even defined. For say this example, you can have B times A, but A times B is not even defined because 2 is not equal to 3. Okay. Yeah. And but even when they are both defined, so if A and B are both n by n matrix, A and B and A times B and B times A are still not always the same. And here we have an example, and let's skip the calculation. So A times B, then you got this matrix. B times A, you got this matrix, and you can just check it out. They are different matrices. Okay. And okay, so this is something different from scalar multiplication because for just numbers, A times B equal to B times A. And anyway, you probably still learn this in high school. And now we have something you might not learn in high school, and we can have a transpose operation. So you have n times n matrix, then you can define n times n matrix that is a transpose of A. So we write it as A to a T. That is, you have the J's element is the H's element, and you are basically swapping row and column. And it's easier to see in an example. So you have A equal to this thing, then you transpose into this. So you kind of swap through diagonal. So this 2, 1 element become 1, 2 element, and this 3 is a 1, 3 element and become a 3, 1 element, etc. So I kind of think this in kind of dynamic way. So you kind of flip your matrix around, kind of turn 180 degrees through the diagonal. But yeah, question. And I guess let's see more example. So you have B equal to this. Then once again you square row and column, so this first row becomes first column, the second row becomes second column, etc. And element wise you can swap through diagonal. So this 4 here you swap through diagonal and it becomes 4 up here. Okay. And we have another example is 1, 2, 2, 3, and then you swap around, then you see you swap around these 2 and 2, you do nothing. So the transpose of T is transpose of C is still the same element. And we're out of time, but I want to say, okay, just this one more thing. And so that's the example of a symmetric matrix. If AT equal to AT equal to A, then it's a symmetric matrix. So basically that means all the off-diagonal element has these pairs, right? Because when they stay over the round, then it should be the same. And it also must be n times n, otherwise the dimension is not the same. Okay. So symmetric matrix is just those matrix with Aij equal to Aji. Okay. So you swap it, so you flip it around, it's still the same thing back. Okay, so that's 1.3, and sorry for overtime. Any question? Otherwise, we'll homework all sometime today. Okay? Yeah. So, I think it's time for the class, right? Okay. See you next Monday.